Now, when we look at the periodic table, we need to start talking about ions. And we talked a little bit about them in our last unit, but we want to make sure we have them officially into our notes now. So ions are a form of an atom that's lost or gained an electron. Okay, so an atom we say is a neutral particle. An ion somehow has become a charged particle, gaining electrons or losing electrons. If we have a positive charge, we call that a cation. That comes from losing electrons, so that's typically your metals. If you have a negative charge, that's from gaining electrons. We call that anions. Those are typically your nonmetals. Now, remember, cations and anions, there's lots of different ways you can do it. I used to have, in college anyway, I used to make up a story about, I had a friend her name was Anne. She tended to be more of a negative person in my life, so that helped remind me that anions were negative. People who are cat lovers, maybe because it's a cat for cation, that's a positive thing in your life, and you remember that being positive. I'm allergic to cats, so that would not work for me. However, cations does have a T in it, and T looks like a plus sign to me, so that might remind me that cations are the positive ones, and anions, or like anti or negative, are negative ones. So however you need to remember that one. Now the cool thing is, the periodic table can actually guide us in terms of some charges. Not for everything, but for certain ones. Okay? And I'm going to show you these here in a minute. One thing you need to remember is that you may have been given a similar guide in previous science classes like earth science or middle school science. And they tend to do more generalizations than I want you guys to do. Okay, so I'm going to limit this a little bit more than you probably have seen before. So if you look at your periodic table, and if I was you, I would actually write these right on the periodic table, someplace where you can remember it and go and look these up. If you are an alkali metal, so all your alkali metals, they're going to be a +1 charge, always. They have one extra electron, so they dump that one extra electron. Hydrogen can be a +1 or a -1, so it can do both, depending on how it wants to ionize. So it's not like the alkali metals, it's a little different. Your group 2 elements, your alkaline earth metals, are always a +2 charge. Okay, so group 1's a 1+, group 2 is a 2+. Now the transition metals in the middle here, they form all sorts of different ions. They're always positive, so you could say a plus sign for all these down here, because transition metals are metals, so they're going to be a positive ion. So they will always lose electrons, but you can't use the periodic table to determine what it will be. Once you jump over to the P group, or the P block of our periodic table, we get to group 13. Now group 13, if you're boron or aluminum, these first two, you only form a 3+. As soon as you start getting into the P elements that also have a d orbital available, then their charges become variable, which means in this first column you can be a 1+ or a 3+. If you are a non-metal or a metalloid in group 14, we don't know what the charge is going to be. You can't designate it. You may have had teachers in the past who said +4, -4, +2, -2. The reality is this. This is carbon and silicone. Carbon and silicone don't really ionize. So carbon and silicone tend to only share electrons. They don't really ionize very often. So giving them a charge is really not a proper thing to do. However, below the stair-step line, the metals and metalloids down here below that, when they do ionize, do so as either a +2 or a +4. Once you get over to group 15, now you're starting to deal mainly with nonmetals. So the nonmetals form negative ions. So in group 15, things like nitrogen and phosphorus and arsenic, if you're above the stair step, you're going to be a -3 charge. So these will all be -3 charge. However, if you are a metal below the stair step, like bismuth and antimony, you can either be a +3 or a +5. So you can ionize to a +3 or +5. Okay. Now, after this point, everything else kind of goes back to regular, because we're starting to deal with these oxygen group and then your halogens and your noble gases, where they ionize very specifically. So oxygen and everything else below that in group 16 always forms a -2 charge. Okay. Halogens and everything that go down the halogen group, remember that's just this group 17, they always form a -1 charge. And then your noble gases do not ionize at all. Noble gases tend to not bond in general, but they do not ionize. So if they do ever form a compound, it will not be through ionization. Okay. Now what this does for us is kind of nice. Alkali metals +1, alkaline earth metals +2, Oxygen group -1, halogens -2, noble gases are 0. Those are all pretty set. A little goofiness in here, but we can talk about that as we go through in our bonding unit, next unit. Okay. So great thing that the periodic table does for us, it allows us to start to map out this ionization a little bit for our ions. Okay. Now we're going to jump to the board and take a look at why would we get these doubling effects down here. Why would we get more than one charge in some of these areas? Okay. Okay, so if we take a look at group 13, and let's pick one element out of there, let's say indium. Okay, so indium, if we take a look at indium, it's number 49 on the periodic table. And if we do its electron configuration, it's a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then it's a 4p1. Okay? So if we take a look at what is going on with our indium in terms of ionization, well, it's not going to ionize anything through here because these are all 1s and 2s and 3s in terms of its orbitals. It's not going to ionize here because that's again a 3. So your 1s, your 2s, your 3s are all safe. No ionization there. That's not the outer energy level. However, we do have two different sets of electrons in the fourth energy level. And if we look, if indium is going to be a 1 plus, well, it can just take away this electron here from the p orbital. If it gets rid of this electron from the p orbital, now it has everything full. So if it has everything full, that's a stable configuration for it. So becoming a 1 plus works really well because it ends up having everything full for its orbitals, getting rid of this kind of partially full orbital. But indium can also become a 3 plus because even though this is a full orbital, wouldn't it be great if we got rid of the fourth energy level altogether? So what can happen is you have a full 1, a full 2, and even your third energy level with that D is completely full. So by ionizing to a 3 plus, again getting rid of these electrons, you also have an advantage in terms of stability. Now the same thing that we just talked about with group 13 with the +1, +3, you can apply to group 14 and group 15. So within group 14, you can do a 2 plus to empty out the p orbital or a 4 plus to empty out both the p and the s orbital. Same thing over here, where the 3 plus would empty out the p orbital and the 5 plus would empty out the p and the s orbital. So in all cases, they're basically ionizing here to remove the s and p electrons and only leave those d level electrons so they have a full energy level at the end. Okay guys, that ends this video. Thank you.